minus 9.7 and 10 to the minus 10 coulombs per meter, if I did it right. That's 110 times epsilon naught, the minus sign. Does the minus sign make sense? Take a look at the picture. Which way is the field pointing? Does it make sense? Yeah, it makes sense because notice the fields are pointing towards the sheet. You got to know it's minus here. If these were positives, the fields would point away from it. I don't know how much is above and below. Yeah.
If we wanted to skip all the vector stuff, could we just do magnitudes and just realize that it's a negative charge at the end? Or do you want us to carry
I'll tell you what, the people that quote, do it the easy way and skip vectors, the trouble is they get right down to here, and these signs start, there's a minus 16 to 50. You can't keep it straight. So the message is, you can't do it if you don't keep track of the directions. You have to keep track. There's no way to do it without, I shouldn't say no way, there are some clever ways with voltage. But you have to keep track of those signs. You have to keep track of the fact that they revert, that they're both going opposite to the dot product. This extra minus sign that came in, right, on both of them. I'm not saying it's impossible. If you've got really good intuition and you know what you're doing, you can keep it straight. But it's very difficult, in fact. And we'll do the last one here. And let's do the last one, and you'll see that these magnitudes don't go in there. So the dominant mistake that people made was they got these signs wrong. That they did not use vectors, that they didn't take the lengths properly, they didn't take the dot products properly. They took 60 plus 50, or 60 minus 50, or 50 minus 60. I got all combinations of sums and differences of those two pieces there. And so it's the trouble is that this is really Gauss's law. It really is vector dotted with another vector. You got to figure out which way these guys go. It comes down to that picture. So the answer is, yeah, if you're really good, you can see it how it goes, and you realize that both of those things will add minus charge. Must be that E times area here, that gave you a minus charge, and E times area here both gave you minus charge. They've got to both give you minuses. You better not have a plus and a minus, right? And that's why they have two minuses signs show up here. But yeah, it's this was not an easy one. In fact, most of this exam was not easy. Let's do the last one. It's actually straightforward. Again, if you just believe in vectors, I'd say it like that. So it asks for, if an electron, which is just, doesn't matter what it is, starts at z equals minus 1 meter, moves to z equals plus 1 meters, so it moves from below to above, how much does the potential change? And so this is, again, one of the main things we use, and not the simplest one, that the change in the voltage, and let's be very clear about where we want to go between. We'll end at 1 meter, and we'll start at minus 1 meter. And it's important to keep those two straight, because when you write this out, it's minus the integral of the starting location. And if I want to write everything out, that was 0, 0, and we said minus 1 meter, it's in the z direction, right? Then we move to 0, 0, say 1 meter. The x and the y don't matter, obviously, it could be anywhere in the plane, but we'll write it formally that way. So this goes with the starting point, that goes with the ending point, and there's this minus sign in front. And then it's E dotted with a change in position. You went from one place, you went from somewhere down here, somewhere down here to somewhere up here, passing through the plane. Right? But we know which way this points, right? Well, sort of. It points in two directions. Up. Up if you're down, and down if you're up, right? So as you pass, so we can't just put one vector in here. We know it's only going to be in the z direction or the minus z direction. So the thing here is that you need to do, and this is part of that keeping the vectors straight part, is you need to write this as two integrals, which are both trivial. So you start at, we'll say 0, 0, minus 1 meter. In other words, z is minus 1 meter. And we'll go up to 0, 0, 0. We'll go up to the plane. We'll go from here to here. Why? Because in that place, the electric field is constant. It's just 50 volts per meter. We'll just write it as, it's E minus. It's the guy down there, dotted with dr. It's a constant that we can just pull out. Right? It's just going to, in fact, this is just going to give us a z component, which is 50 volts per meter times dz. And then the next part, again, minus sign, we have to continue the integral, in this case. You continue the integral from where we left off, 0, 0, 0, up to the endpoint, 0, 0, 1. And again, it's now going to be E, not down here, but E up here, in the plus part, dz. So that looks maybe a little bit complicated, but it isn't. Why? Because the first integral has just got a constant electric field of 50 volts per meter in the k-hat direction. So that's going to give us, we still have a minus sign in front. This is 50 volts per meter. And that's in the k-hat direction. So this is going to be k-hat dot dr. That's just going to give us dz. We integrate dz between here and here. Right? That's just going to give you 1 meter. That's a total distance you traveled in the z direction on that first part. You started at -1, you went up to 1. Changes 1 meter. And if you don't believe it, you can just integrate dz between -1 and 0. Very similar story here. The minus sign. Then this will give us, this only has a z component up here. It's minus 60 volts per meter. So that's minus because of this minus in front. And then the minus here, because the z component is minus 60 volts per meter. And again, we went from 0 up to the final point of 1 meter. That was the total change in z, just 1 meter. So doing that integral, the remaining one, this again just gives us times 1 meter. All right, now, if you look here, you see there's a minus minus. That's 60 volts times 1. And this is minus 50 volts. 60 minus 50, that's 10 volts. First times 1 meter, right? So the meters. And so in this second one, this is what I meant about those components, right? In the second one, notice that those two things subtracted. When you do this integral E dot, the path, it mattered that part of the way you're going in the direction of the electric field, hence, moving towards the plane, and in the other part, you're moving against it, because it cares about whether you're moving in the same direction or against the field. In the other case, where we work through the charged unit area, those Gaussian surface, the normal reversed and the field reversed. And that's why in the first case, you ended up, if you will, subtracting off both of them. And so that's what makes it a little bit nastier for sure. I mean, you really have to keep track of the direction. You have to respect the fact that these really are dot products. It really is, caring about, as you saw, these different things. So, any other, was it easy? Yeah. Okay.